Hi, it's Terry Denery at the MathWorks. So in this video, we're going to talk about forward dynamics, meaning that we're going to solve a differential equation for I'll call it the angular acceleration of our motor. And we're also going to talk about faster simulations that are made possible when you're working directly with the equations of motion. It's ultimately the calculation's easier because everything's explicitly represented properly. And that's all possible because of these great symbolic approaches applied by MotionGenesis to generate these equations. So anyways, with regard to our input deck for MotionGenesis, this is the key point right here. Instead of solving for the torque, we're solving for that angular acceleration. And let me show you my use of that code in the model we have right here. And I think I'll run the model first, all right? And let's maybe run it from the Explorer, and we'll just hit run. Oops, that's a previous one. I've made some changes, so let's redo this. I'll just shut that. And the changes I made was to take the mechanical linkage from its initial position. We know it's essentially like two little inverted pendulums, and we're going to just give it a little bit of a push. And so the little bit of a push is a torque that's going to be provided by the step function. It's going to be a duration of 1 second, holding a value of, what's that, like 10 to the minus fifth Newton meters. So anyways, let's hit run and see what we got. Oops. Let's do this again, this time with, we're going to turn this off in a second, but for right now we want it on. It's called the Mechanical Explorer. It's part of Simscape Multibody, and it's the piece that provides the animation. So anyways, let's run it again. We'll look at it from that view. Okay. I don't know, I just kind of like looking at that, and I think it's really kind of cool how it dwells as it tries to hold that equilibrium position, in that vertical orientation, but it can't quite do it. So anyways, but let's look at our model. Okay. And you're going to see that we're comparing Simscape Multibody with the solution provided by MotionGenesis, and that we're tracking both position and velocity, and clearly position, it's dead on. And we'll see the same thing on velocity. So essentially two curves are there. It's the blue that's on top, but there's both blue and yellow for each of the two tools. Okay, they're both being fed that same torque, and I want to show what it looks like on the MotionGenesis side. All right, and here's what was generated for us, ultimately giving us the angular acceleration with that term, and it's passed in and out of the function by the function statement we see right there. And the calculation, of course, requires kind of the current state of the system, which is generally provided by the things that are being passed in here. And there's this whole kind of dependency issue and dealing with the singularity where the linkage can have the exact same lengths, the exact same joints, and the joints occurring the exact locations, but the initialization is set one way or the other. There are two essential, I'll call it possible results for how this mechanism will move. Anyways, it's something we talked about in the last video, and if it's confusing at all, go check that out, and also possibly send me an email or something, let me know. But anyways, I think it's explained pretty well. But speaking of kind of dealing with the two configurations, it's handled on an initialization level, and it's essentially we're making our choice for which of those two forms we want. The one we're choosing is the one that is represented accurately in the initialization of the Simscape Multibody the SimWise model by this configuration. So when I set these two angles right here in that integrator, they're each set to 0 by our choice to define the problem that way. And that occurs in these two integrators right there and right there, right? So clearly it is a 1 degree of freedom problem. It's mostly the motor, and so we drive torque through the motor and we solve for angle and angular velocity with our double integrator right there. Okay, So anyways, great that we're getting good correlation between the two. Let's try a little bit of a tougher problem. And instead of it being 1 times 10 to the minus fifth Newton meters, let's make it 1. And we'll hit run. I want you to see kind of the progress of this. It's going much slower in calculation, although the linkage itself, and you'll see it right here, is going much faster. I think I'll shut off the animation. You'll see it'll start moving a little bit quicker. All right. And we're going to see that blue is on top of yellow, and we're reaching a very high accumulation on the angle. So it's gone, we're up over 2,000 radians. So what's that? That's quite a few revolutions. I'll just say it that way. Okay. And it's real interesting to look at the velocity, which we see right here. And it is a step function, and we're seeing essentially two clear bounds, and certainly there's essentially an exchange of kinetic energy for potential energy. There is no dissipation because we're not modeling friction in the joints, and so it just keeps on oscillating between a high, let's call it a high kinetic energy position and a low one, but oppositely, low kinetic energy is high potential and so forth. So anyways, let's just kind of zoom in, and it's beautiful how well the two solutions work so effectively together, and they're producing the same results. And I did plot this, which I think actually is a good thing to look at. All right, let me change my style. I hate it when it automatically adds markers when I don't want them. Okay, and I'll just say that it's reaching right now 70 rotations per second, which is pretty fast. And I'd say from a validation point of view, I think I'm pretty good with what we just looked at. I'm sure you could be much more exhaustive and just kind of proving the two are the same, but I think that they are, and I think that this certainly gives you plenty of evidence to believe that they are. Okay, but what I do want to address right now is that the simplification as is made available by direct solution of the differential equations, it's a really important computational thing, right? And so I think the way I'll do this now is let me hit save on this. You'll see the name of the file is called small 4-bar. And I'm going to go to my MATLAB space, and I'm going to run this command. Okay. Okay, this is the thing that's kind of driving me crazy. So we're going to do this over in a second. Let me actually hit this. Don't know why it brings it back. The Explorer. Oh, actually, I had it on. Okay, so that's my error. But, okay, we're gonna just have to wait for it. All right. So I don't have access to the stop button, and I think it's gonna be maybe like 20 to 30 seconds. So 27 seconds. All right. So it's probably a good thing that this happened. And so what we're gonna do now is let's go turn off the Mechanical Explorer, and we'll see quite a bit of that time is consumed through the animation piece. And so we'll remove that check mark right there. I always think it's a good idea to save. So let's save it. Okay, and let's run this command again, tick-tock. And if you don't know about it, I love this functionality. And there's two functionalities that work here that I think are both important. One is the sim command, which means you can run any Simulink model you want from the MATLAB command line. So that's what we got on the middle. This tick-tock, actually, tick is something that essentially starts the clock ticking, and tock ends it. And so as it runs this simulation, we capture how much time it took my laptop to run this simulation. And so I think it's going to come in maybe around 20 to 21 seconds this time. And so it's going to be faster because we're not animating it with the Mechanical Explorer. So let's wait for it. It's almost there. I'm sure we're going to see. Oh, shoot. My error. I didn't hit the enter button. Anyways, it is going to be about 20 seconds. I think if we have that model open, is it done? There it is. Okay, so 20.9 seconds. All right, so now we're going to comment out the entire mechanics part, the Simscape Multibody part, which is all this upper stuff right here. Right, and I'll hit save again. And we'll do that whole tick-tock command thing again. And this time we don't have to wait so long, 1.22 seconds. So clearly there's a major advantage in running it with the direct solution to the differential equations with regard to getting speed. And I'll do one last thing so that this will be a fair comparison, is let's run the Simscape Multibody version all by itself. And so we'll uncomment this, but we'll comment out the direct solution to the differential equations. And let's hit save. And here's the thing I was going to mention. It does kind of drive me crazy. Is that model settings? When I uncomment it, check that thing back for me, and I didn't want that. Okay, so let's hit save. Let's run tick-tock one last time. Okay, and this time it'll be purely Simscape Multibody, right? And so we're going to see, again, there's this really important speed advantage is available through the direct solution to the differential equations, right? And so I'm happy to show this at this point without feeling I'm diminishing the usefulness of Simscape Multibody. I'm really think what I'm showing here is the complementary nature of the two solutions, right? And so the mere fact that they're both coming from the same general mechanical description as was defined in the SimWise model, and proving that they predict exactly the same results for this problem means that they are equivalent solutions relative to accuracy. Okay, now one has clearly this advantage of running super fast, and that's a great thing. We should be thrilled that we have something that runs as fast. But then I'll also say the fact that we have a Simscape multi-body model that we can dive into and really understand the nature of what we're looking at, and we can see the solids and see the joints and all that sort of thing. I love the schematic language of Simscape Multibody, and I love the ability to go in and really kind of tweak things interactively the way I want to. And then finally, I do love the animation that comes with the Mechanical Explorer. You know, that mechanics is a very visual thing, and having that opportunity to see how it moves is always going to be important to me, and I think probably to almost any engineer. So anyways, to wrap up, I think we saw two things in this video. One is that the two converge to the same results, really, really important. And then the next thing, which I think is super important, is we have an opportunity for an extremely fast running simulation when we translate to a direct solution to the differential equations. So anyways, thank you.